Hey subscribers and people investigating flat earth. Often you see that flat earthers do laser tests and all kinds of tests, show pictures of a curved earth, etc, etc. But the question they never ask, and that is failing always, is how would it be if the earth was flat? Because that's what they believe, and you never see that. So they attack a globe, but then do not show what it would be on a flat earth. And what would it be? Is there even refraction on a flat earth? Let's have a look at people who do it wrong. For instance, the people from FE Core, but basically any flat earther does it wrong. For instance, Flat Earth Core Inc., the so-called organization dedicated to accuracy, discovery and application in scientific research. Now, I've already done videos about these frauds. Basically, they're not even engineers and they should not use these names, and certainly they are not scientists. They don't even have an idea how to do it. But also they, in their experiments, use this whole refraction in the wrong way. They have this laser level experiments they did, and always funny is that they use a globe model for all their calculations or whatever, where I would say if I'm going to prove that the earth is actually flat, yeah, my model would be flat and everything is based upon the flatness and not about a curve. So what goes wrong then is, although they do some temperature measurements, they do them basically based on a number of positions, but not on altitude above the water. And then in the end, they, as they say here, they have information they gathered, and that all looks very nice and scientific, and then they use Snell's law. Now, if there's one thing you cannot use with refraction, is Snell's law. And the second thing you can't use is it on a flat earth, because basically there is no refraction on the flat earth, as we are discussing in this video. So even these guys do it totally wrong. So what is all this refraction people talk about? That is what happens with light when it bounces off and breaks through water. We all have seen glasses where you put a straw in and then it seems as if the straw is broken. And you can simulate that here very well. It also happens when you have a difference in air density. But as you can see, the effect is much less than on water, or if you can play around here with glass. So with air it can happen as well, but it does require some pretty strong temperature differences to cause air from a different density. However, you still need something that doesn't or almost never exists in nature, and that is a hard border between the air of less density and the air of more density. That is one of the points why refraction in this sense, as happens here with water, glass, does not really happen in nature, does not really happen in the air. We'll come back to that, but this is basically the Snell's law, and it was, of course, what else could it be, a Dutch guy, Willebrood Snell van Rooyen, who found out this and gave some formulas to calculate with it, as you will also see used by the FE Core in their calculations, but senseless calculations, because we don't have fixed hard borders in the air. What is also important is that the moment we are not crossing any line, the light will go straight. That is also very important. And if you come from above, you know, up to certain angles, nothing will happen as well. Yeah, and that's also very good to know. So if you go from less dense to more dense air, from above not much happens, only later. You see, you really need to go down and then something starts to happen. But basically, going from light to dense air, nothing happens. You could turn the whole picture 90 degrees now, and then you come to the point where people say, yeah, but I'm farther away, so the air is denser in between and therefore the light must break. No, if you go straight down, nothing will change, not even if you go through glass. So the biggest mistake made by people like Johannessen, etc., is that farther away should give you denser air, and breaking, no, it does not. As you can see, the light goes straight. The amount of air does not matter at all. And for the Snell's law, you actually need a fixed border, which is not available in nature, unless you have an inversion layer, which is a rare atmospheric condition that sometimes happens, but we're not discussing that. We keep it simple. Keep it simple. Let us listen to a nice thing Voice of Reason prepared.
This will increase the air density gradient, since cold air is more dense than warmer air, and therefore we see even more refraction over cold water. And unlike the water-to-air transition, which bends the light abruptly, the atmospheric density gradient is gradual, so the light bends slightly and gradually, which forms a curved shape. Now here comes the part that is counterintuitive. The light rays are bending down, but this makes things actually appear higher than they are, not lower. Think about it. The light is bending down toward the Earth, so when we look at that light, it looks like it's coming from a higher point than it is.
Now, how much higher it looks to be, or seems to be, based on a more gradual change in density of the air, could be calculated with Fermat's principle. Fermat was a French mathematician who basically said that the path taken between 2 points by a ray of light is the path that can be transversed in the least time. And that led to the Snell's law. If you want to calculate with it, then you have to use this gradual change, and you end up with calculus. And it's, for me personally, very long time ago, more than 40 years, probably 43, 44 years ago, that I actually used it. And then more for quantum mechanics than for this type of calculations. But you would end up with this type of calculations to figure out where and how high it would seem to be. But you don't need to. On a flat Earth, you don't need to. Let's have a look. So when we now take all this knowledge, then if the Earth is flat, we have of course a flat surface, and above it there might be a number of layers of different temperatures. In fact, actually, it would be a gradient. Gradually this would happen. But just for visualization, it shows that when you then do a laser test or looking over a lake, all that utter nonsense of refraction, taking care that things disappear or it looks as if there is a bulge in between on a flat Earth. No, on a flat Earth, light does not bend there. It does not cross any temperature levels. However, if you look at very high buildings, of course the top of the buildings, that light would cross through some layers. But what it however would do is, if this is the actual building and we follow this line and then at one point it bends down, it means that it actually looks higher, as we see in the video where the top of the buildings seem to jump. So the top of the buildings could jump a little bit higher, a little bit lower, depending on the changes of the temperature layers that are higher than my eye level. But the part of the building that is at my eye level and that is here behind the curve would on a flat earth be at eye level with me. Yeah, the building should be much higher up, and then still the tops like here could jump a little bit, but they should be above my eye level. That happens when these layers, or the gradient of these layers, changes over time during an evening. But basically, if you look flat parallel over a flat earth, you're not crossing any temperature layers, and you should exactly see that. So nothing can ever go behind a curve, a bulge or whatever on a flat earth. There is no refraction in the line of sight at eye level. So the tops may vary. If it's a mountain or a building, the tops may vary. If you are on top of a high hill yourself, you might find some changes below, but at eye level there should hardly be any changes, as we have seen with the simulation. And that means there is no reason whatsoever to use refraction in formulas when you do laser tests. It's nonsense. The only thing you need to do is take care that your laser and eye level are approximately at the same height. Or you just take a lamp and you look at the lamp, because using a laser is silly in itself. And that's it. And on a flat earth there should be a parallel line to the surface. You're not crossing any temperature gradients or levels, and therefore it should be a straight line. Nothing disappears due to refraction, because it is not happening. So with the knowledge we have now, we can do one other thing. Suppose we're here somewhere in the United States, it's summertime, let's say around Quebec. In Canada is also a nice point, it's here. And it's midnight in the summer, then the sun would be here at the Tropic of Cancer. And the distance would be approximately 12,000 kilometers, and the sun is 5,000 kilometers high. So let us see what angle the sun would be. This is 5, this would be 12 kilometers. We calculate and we see that the angle A, the angle at which the sun would be, is 22 degrees. So we take this same tool. I've now taken that one from here, and then you can apply it. And what we then see, if we go to 22 degrees and a little bit, that is the height at which the sunlight would enter the atmosphere, depending on how thick the colder part of the atmosphere is. It will bend more down, always more down. You know, if there would be the same atmospheric density, then we would see the sun straight up at that angle. When there is more density of atmosphere, and we follow this line, the sun should look higher, like the buildings we saw. Tops should look higher. Everything through refraction should look higher. So the sun can never set. Even if we go as far as thinking that, suppose we are here somewhere at the Tropic of Capricorn, and it is winter time in the northern hemisphere, and then the sun would be over the Tropic of Capricorn here on the other side, and that would be approximately 25,000 kilometers far away. So we reset, we say the sun is 5 kilometers high, 25,000 kilometers far away. we still have an angle of 11 degrees. So we would get this. And as you can see, again, if there was no difference in thickness of the atmosphere and there was no temperature gradient, we would have to see the sun still up in the air. The moment there is some form of refraction, because the air close to the Earth is denser than high up, which is always the case, we see that in an extreme case, and we follow the light as we think we would see it, the sun would only appear to be higher. And so in general, the sun light, when it is right above you, suppose you're on the equator at 12 noon, and then the sun moves away, and you see there is no refraction, nothing is happening. And then slowly something is happening. Let's make it a little bit stronger. The refracted light is slowing behind the actual distance of the sun. That means the sun is higher than what it appears to be. But it can never be lower than 11 degrees. And if you're living in the northern hemisphere, usually it will be around 20 degrees. And therefore, on a flat Earth, the sun can never set. Period. I hope you enjoyed these explanations, and looking forward to constructive remarks in the commentaries. Thank you.